Hello, so in this video I'm going to talk you through the idea of a function. Now actually, out of all of the videos that I'm going to record and you're going to watch in this module, I would argue that this one, the one on functions, the one you're watching right now, is probably the single most important one to watch because it covers a really fundamental and central idea in all of mathematics. Okay? If I ask you the question, what is mathematics? Can I ask you to pause the video for 30 seconds and just think, what does mathematics mean to me? So do that now. Pause the video and think, what do I think mathematics is? So hopefully you've had a chance to pause the video, okay? I'm going to tell you what mathematics means to me. So mathematics is a language which describes the connections and the patterns which exist in the world around us. Okay? And it just so happens that once we've noticed those connections, those patterns, we're then able to generalize it and make it abstract and ask questions like, why does that make sense? Or what if this were the case? And that's how mathematics grows, okay? So functions are pretty much the central idea in the whole of this course. And if you can understand functions, it's going to help you to understand future concepts. Now, I will say that even though functions are really important, they're not necessarily going to be the questions in an exam which are going to give you the most marks, okay? But nonetheless, that doesn't invalidate what we're doing in this video, okay? So really make sure you get your head around what's happening here. So I've talked about enough. I've talked about the importance of functions and why this is an important video, but let's actually get started and define what is a function. So in a single sentence, a function is quite simply a rule that connects inputs to outputs. Okay, so it's a rule that connects inputs to outputs. So let's have a look at this. There's three kind of key terms that I need you to get your head around. The first one is the rule bit. Okay, so a rule, it could be something like multiply by 2 or add 3. Or make sure the output is always 5, okay? Or square your input and then add 2, okay? These are all examples of the rule, okay? And this is really the function, okay? So the function bit is really the rule, okay? It's the multiplying by 2 or adding 3 or squaring and dividing by 7, for example, okay? We then have two keywords over here. So we have inputs, okay? Now notice that inputs is made up of kind of two words smushed together, okay? You've got in and you've got put, okay? So really, if I just swap those two words around, I get put in. So an input is a value that I put in to my function. And in the same way, if I look at outputs, notice that that is made up of two words. It's out and put, and we smush those together. Again, if I swap those two words around, I get put out. So in other words, it's the thing which gets chucked out the other side of my function. Now, I wouldn't mind betting money that you've already met this idea before in one form or another. And you probably noticed it in the form of a machine like this. So if I just draw a very, very crude kind of a function machine down, you might have seen something like this, perhaps several years ago now, but I wouldn't mind betting money again that you have seen something like this. And the idea is that on the left-hand side, you chuck values in. So because we're putting values in to this function machine, I would call that an input, okay? And then on the other side, so in other words, in the middle, I'm doing something to that input. That's the rule part. That's the thing which I'm changing in the middle. So I'm taking my input, I'm doing something to that input, then I get a value out the other side. Well, if the function machine puts out a value the other side, we're going to call this an output, okay? So really, the bit in the middle is my function. It's the thing which is actually changing my input to get to my output. Now the rule, or the function, is always the same, okay? So it doesn't change halfway through depending on different values, okay? So the function is always the same, okay? So for example, in this case, let's suppose that the rule is add 3, okay? So that's my rule in the middle, that's my function. So whatever input I put in, and it's a number in this case because it's mathematics, I must add 3 to that input, and then my output will just be 3 more than my input. Okay, so as an example, if I put 7 on this side, so I put 7 into my function, it then changes, and on the other side, I should get 10. Okay, if I put -5 on this side of the function, it then changes, and I should get -2. Okay, I can even put really big numbers like 1,000 on this side. And if I put it into my function, my output should be, you've guessed it, 1003. Okay, so you notice that all of these numbers are connected. So the 7 and the 10 are connected. The -5 and the -2 are connected, and the 1000 and the 1003 are also connected. And the way that they're connected is they're connected by this same rule. They're just adding 3. So on the left-hand side, I get my inputs. On the right-hand side, I get my outputs. Okay. So this is really the goal of a function. It's a way of changing a value to get another value out, but the thing which is changing is always the same each time. So in this case, I'm adding 3. Now, I would argue that actually, this is quite clunky notation, so I don't want to keep on writing input all the time. I don't want to physically write that word all the time. And the same with output, I don't want to have to write that. And also, this kind of notation in the middle, the adding 3, that's kind of quite long, and particularly if I have long complex functions where I have to kind of like add 3, then subtract 7, then square it, and then divide the whole thing by 5. That's going to take a long time to write out. So because I'm a mathematician, what I'm going to do is I'm going to use some notation. Okay, so I love notation. Really, all of mathematics is about trying to express really fundamental and important ideas that you've noticed in a really succinct and clear way. Okay, so instead of writing input, we generally give this a letter. Okay, so just for the moment, I'm going to call my input X. Okay. So my input, I'm just going to call X. So rather than writing the word input all the time, I can just now deal with X. Okay, it could be any letter I like, but in this case, I'm going to call my input X. And I guess because my output comes after my input, so after I put it through my function, my output comes afterwards. Well, what comes after X in the alphabet? You've guessed it. Y. Okay, so I'm going to give my output the letter Y. Now again, these could be any 2 letters I like. It's just by convention that we tend to just use X and Y. But it's important to note we don't always have to stick with X and Y. Okay. Then what can I do with this bit in the middle? Okay, so this function notation. Well, I guess I could give my function a name, and I guess because I'm giving my inputs and outputs letters, let's give my function a name as well. So for the moment, I'm going to call it F for function. Okay, so that's my F there. I might just curl it over to make it a little bit clearer. Okay, so that's my F. I'm just giving my function a name and I'm just calling F. But again, I could call it whatever I like. I could call it G, I could give it H, I could give it Eric if I wanted to. I'm just simply giving my function a name. Okay, so in this case, I'm giving my function X. Okay, so the way which I would write this is that in order to get Y, okay, I'm going to have to apply my function to X. Okay, so I'm going to have to, in order to get Y, I'm going to have to apply my function to X. So in other words, I could say that Y is equal to, it's the same as, that's how I get Y, okay? I get it by applying my function, which I'm giving the letter F, to X. So the way which I'm going to write that is I'm going to write my X in a bracket, okay? So you see, this is really important here. This thing which I've written in green over here, the way which I get Y is applying my function to X. So you notice that inside the brackets, I have my input, okay? And then the F goes on the outside because that's the name that I've given my function. Now this does not mean, okay, so the F of X, this does not mean F times by X, because usually in maths when we see a bracket, we mean times, right? Not in this case. In this case, I mean F is being applied to X. So I'm applying a function to an input which I'm leaving the letter X, okay? The way which I would say this, okay, so if you're interested in kind of how I would verbalize this, I would say Y is a function of X. Okay, so Y is a function of X. So the way which I get my output Y is by applying a function to my input X. Okay, if you prefer, I can even shorten this further. I can say Y is equal to, in this case, I'm giving my function the letter F. Okay, so I'm calling my function F. So I'm saying Y is equal to F of X. So I could say that as well. Okay, so these two things are the same regardless of how you say it, okay? It's just basically how you communicate it. So you can say either Y is a function of X, or you can say Y is equal to F of X. That's fine, okay? So you can say either of those things, but it's important to understand the idea. All I'm literally doing is chucking inputs in, and I'm giving the letter X to represent my input, and then I'm applying a function to it, and again I'm giving letter F to represent the name of my function, and then I get my output, which again I'm calling the letter Y just for convenience, okay? And then I can write that as Y equals F of X, or Y is a function of X, Okay, so this thing up here in the right-hand corner. But you notice in this case that I actually have my rule, okay? So my rule for my function is adding 3. So the rule for my function is adding 3. So I could actually say that even though this statement is absolutely true, this statement I'm using to connect my inputs to my outputs, and the way that I do that is by applying some function f to my inputs. But I could actually say that my function, my f of x, so my function of x, okay, which I could write as that. So my function of x is actually equal to, well, have a look. What's happening here? Well, I'm taking my input, then I'm adding 3, and I get my output. Okay, so in other words, my function is just simply taking my input and then adding 3. That's literally what the rule is telling me. So I can say that f of x down here, I can say that f of x is equal to taking my input, which remember I'm giving the letter x, and adding 3 to it. So I can say that f of x is equal to x plus 3. Just simply want you to think of that is my input is x, and I get my function by taking that input and adding 3. Okay, so that's really, really crucial and important. So, okay, now we've got the idea of the notation in our head, okay, we can basically say that if y is a function of x, in other words, my output is y, my function I'm calling f, and my input I'm calling x, okay, and I know that my function, f of x, is equal to my input plus 3, or just simply x plus 3, then I can write this more neatly. So I don't need to now draw out that big, horrible kind of function machine. Okay, I don't need to draw that out every single time because it takes time, and I don't need to write all my inputs underneath like I've done there. I can just simply work with this notation and people would understand what I mean. I'm saying that my output y is a function, which I'm giving the name f, of x, my input, okay? And the way that I get my output is by taking my input and adding 3, okay? So these are the two kind of key statements I need to write. So if I, for example, wanted to work out what f of 5 was, okay, if I wanted to work out what f of 5 was, well, just remember that the thing which goes inside the brackets, so remember f is just the name of my function, the thing which goes inside my brackets, in this case, I'm saying it's 5. Well, just remember the thing which goes inside my brackets is simply just my input, okay? So in this case, my input is 5. Well, how do I get my output? Well, I just add 3 to my input to get my output. So what is 5 plus 3? Well, 5 plus 3 is just equal to 8. So that there is my output, okay? So let me just write this in. The thing inside my brackets is always my input. We've seen that before, okay? That's how we agreed we should write our notation together, okay? And then whatever answer I get out after I've applied my input through my rule, in this case adding 3, okay? This should now be my output. So in other words, my output is 8, okay? If I asked you what was f of -1, okay? Well, just think the way which I get, well, what's my input in this case? My input in this case is -1, so that's my input there, okay? Well, how do I get my output from my input? Well, just remember, I just apply the rule. In this case, my input is just added 3, and then I get my output, okay? So in this case, if I take my input, which is -1, I add 3 to it, I should get my output. Well, that's 2, right? That's 2. So that there would be my output, okay? Let me just try with one more example. Let's try, for example, with f of 0, okay? What would f of 0 mean? Well, just remember, what is my input? My input is always the thing which goes inside the brackets. So in this case, my input is 0, okay? How do I get my output? Well, it's still exactly the same rule as before. I just have to add 3. Okay, so let's have a look. If I take 0 and I add 3, well, I just get 3, right? So therefore, the number which I get out is 3, so that is my output, okay? Does that make sense? Okay, so the notation which I'm using, this y equals f of x business, just go over it again, this y equals f of x business is basically saying my output y is achieved by applying my function f to my input x. Okay, that's simply all that means, right? And the way which, the rule, my function, is just simply taking my input, which in this case is x, and adding 3. Okay, does that make sense to everyone? Okay, hopefully it does. Okay, so what about now if I give you 2 different functions, okay? So I have 2 different functions here, and you can tell that they're different because I'm actually giving them different letters, okay? So you notice, let's just break it down. Let's have a look at the thing in red first of all. So the thing in red, we have f of x equals x squared. Just remember, what does that mean? Well, f is the name of our function. Okay, so f is the name of our function. So it's a way of differentiating the red function from the blue function because we're using different letters. So on the right-hand side in the blue, the name of my function would be called g. Okay, so f and g are different functions. They're just differentiating the two by just giving them different names. Okay, but the thing on the left, the thing on the red, okay, the input is x. Okay, and the rule that I'm using is x squared. So what does that x squared literally mean? Well, remember, x is my input. Okay, I've already established that. X is my input. So in other words, I'm taking my input, the x, and I'm squaring it. So just have a look. What am I doing? I'm taking x, that's my input, and squaring it. Okay, so therefore my rule is square it. Okay, so I'm just going to write it down here. So I'm going to square my input. That's the rule for the red function. Okay, that's the rule for my function f. Have a look at the function on the right, the one in blue. Okay. Well, just remember again, the x just means that's my input. Okay. And have a look what I'm doing to my x. Okay. So my x, I'm taking away 2. Okay. So in other words, my rule for my blue function, the one on the right, the rule for my blue function is subtract 2. All right. So it's nice and simple. I just have 2 functions there, okay? So I have a function called f, I have a function called g, right? The one on the left, my f function, I'm just squaring my input, and the one on the right, my g function, I'm just subtracting 2, okay? That's all that notation literally means. So now let's suppose I want to do something funky. Let's suppose I want to do f of g of x, okay? So this is looking new, okay? I want to do f of g of x. So let's just break it down. Let's start with the innards first of all, okay? So first of all, you notice that f is my function, okay? And then what's my input for my f function? So just have a look at my f, okay? Just remember the input always goes inside the brackets. So that there is the input of my f function. That there is my input. In other words, the input to my f function is just another function. It's just in this case, it's g, okay? So my input is another function, g. And in this case, I know what g is. It's this thing up there, okay? So it's just subtract 2. So in other words, I could write this, if I like, as this is equal to, let me just put it back to black, this is equal to f of, well, instead of writing g of x, let's actually write what g of x actually is. It's x minus 2. We've got that up there. The x minus 2 bit is up there. So in other words, this is x minus 2. Do you see that? So all I've literally done here is I've just substituted that g of x with what it actually is. It's just x minus 2. Okay? So now I'm in a good position. Now I'm in a good position because I know that I just need to taking f. Well, I know the rule for f, okay, it's just squaring it. I established that at the start. And what's my input in this case? It's x minus 2, okay? So just remember the rule for f is just squaring it. Square whatever my input is. And in this case, my input is x minus 2. So because the rule says square my input, then that's more than happy to oblige there. Take my input, in this case it's x minus 2, and square it. Okay, so that there would be f of g of x, okay, f of g of x, right? So let's just expand this out, make it look a little bit prettier. Well, if I expand that out, I get x squared minus 4x plus 4. So that there would be f of g of x. Now, that's what it means from a notational point of view. But what is actually happening here? What's actually happening? Well, what I'm simply saying is first of all, I work from the inside. So first of all, I start with an input called x. Okay, I start with an input called x. Then I apply g to that because you notice g is being applied to x. Okay, g is being applied to x. So first of all, I apply g. Okay, then once I've got that, so I'm currently sitting here in my chain, I then need to apply f to all of that. Okay, so I apply f to all of that. So then I put all of that through f. Okay, and then I get my output. So then I get y. Okay. So in other words, what this is literally saying, if you want to think about it as a chain of functions, in fact, we call this a composite function or a chain of functions, because you're literally taking an input and first things first, you're putting it through the function g. Okay, so if I call my function g here, So my function g in this case is subtracting 2. That's my rule up there. So I first of all put it through g. Okay, so I subtract 2. Then I put it through f. So I put it through my next function then. And my function for f, just remember, is squaring it. So I take whatever that is and I square it, okay? And then I get my output y. So if you like, what I'm literally doing here is putting it through one function, then another function. And I can keep going like this as many times as I like. Now, let's actually just focus. Let's focus on this part here. Let's actually focus on this notation, because I still think it's a little bit clunky and I still think we can tidy it up a little bit. So at the moment, I've got f of g of x. So you always start with the x. You always start with what the original input was, which in this case is x, and then you work outwards. Then you go through g, then you go through f, all right? So you always start with the x and you work backwards. You work to the g, then you work to the f. So you do it in that order, okay? But you can imagine, I just said that because it's just simply taking an input and then applying it through multiple different functions, one after the other, you notice that I could write this as like 10 different functions, one after the other. Well, in that case, there's going to be loads and loads and loads and loads of brackets, which I think will look really, really busy, okay? And I don't think it will be the clearest thing. So what I'm going to do instead is I'm actually just going to get rid of all of the brackets apart from the bracket around my original input, okay? So let me show you what I mean. So instead of having two pairs of brackets, so one around the x, then one around the g of x, okay, I'm actually just going to write one set of brackets just around the original input x. So in other words, I'm just going to write f g of x. So this still means exactly the same thing. It still means take my input x, then put it through g, then put it through f. So this is the first thing I'm going to do, this is the second thing I'm going to do, and this is the third thing I'm going to do. So first of all, take my input x, then I'm going to put it through g, then I'm going to put it through f, okay? But instead of writing all of these brackets one after the other, I'm going to remove all of the brackets apart from the ones around my original input. Well, the original input was x, so I'm going to keep those brackets in there, but everything else I'm going to remove the brackets. So they mean the same thing, okay? And it's really important that you're aware of what this means. So we usually write it like this on the right-hand side. We usually mean here, x is our original input, then we put it through g, then we put it through f, okay? So actually, if I now create more and more functions, if I write something like this down, f, g, h, i, j, k of x, okay? Just have a think. What function will come next? So f, g, h, i, j, k, they're all functions, okay? They might be different functions, they might be the same function, doesn't matter, okay? They're just functions. So each letter which I've written down there just represents a different function, okay? Then the idea is that I would start with x, so that's the original starting point. Then I would put it through g, then I would put it through k. So I'm working back outwards. So the next function I'd put it through is k. Then I would put it through j. Then I would put it through, you guessed it, I. Then I would put it through h. Then I would put whatever I get out from that lot, I put it through g. And then finally, once I get an output from all of those things, I put it all through f as well. Okay, I'd put it through f. And then I would get my output over here. So actually, instead of writing x and y, I'm just going to write input. I'll put x in brackets. And now this side, I'm going to get my output, which in this case is going to be my y. Okay, so hopefully that makes sense. This is the idea of a composite function. It's basically one function. You start with an input and you apply it through one function, then another function, then another function. So functions one after the other until you finally finish with your chain or your composite functions and you get an output down the end. Okay, so hopefully that makes sense. Okay, so let's talk a little bit more then about how we can actually physically represent functions. Okay, so let's suppose I start off with a function here on the screen. Okay, so I've told you here that my output y is, I achieve that by taking my input x and then applying it through a function f. Okay, that's what y equals f of x means. Okay, and in this case, the rule, my function, is just 1 over my input. Okay, so as an example, if I asked you for f of 3, okay, that would be 1 divided by 3 or 0.3 recurring, however you wanted to write it. Okay, so that would be my output. So if I take my input 3, put it through my function, I should get 0.3 recurring or a third as my output, okay? So hopefully that makes sense. But what if I wanted to find a way of connecting together all of the different possible inputs and all of the different possible outputs? Well, one way that I could do that is doing it graphically. So here's what I'm going to do. I'm going to bring this screen up here. Now, this is going to come to my GeoGebra page. If you're interested, you could either go to this link or you go to my GeoGebra page, which is GeoGebra Maths Partner. Okay, but this is basically what I want you to see. Now, it's going to take a little bit of setting up or a little bit of explaining what's going on here. So you can see that in the top right hand corner, I've effectively got my function set up. So this is my function f of x and it's 1 over x. And the idea is that I have two number lines on the screen. So there's one number line and here is another number line. Okay, and these are just straightforward regular number lines. So all of the real numbers can be at a unique position along this real number line. Okay, so there's the 0 in the middle, then you've got 1, then you've got 2, then you've got 3, then you've got 4, and you've also got all the negative numbers, -1, -2, -3, -4. And you can see that this is the same kind of principle on the output number lines. These are two separate number lines. The idea is that the top number line is going to represent all of my inputs. So I'm basically just going to pick a number from somewhere along the top number line. That's going to be my input. And then I'm going to see where it will end up on the bottom number line, which is going to represent an output. So you can see, for example, in this case, that I'm just picking the input 1. So you see this sort of blue circle here. This means that I'm picking the input 1, I'm putting it through my function, and I'm seeing where it would end up at by mapping it to a position on the output number line. Okay, so you can see in this case that fairly obviously if I take my input to be 1, if I do 1 divided by 1, my output should also be 1 as well. So my output is kind of given by this orange circle, and you can see I'm just mapping it together with this kind of arrow. Okay, but you can see that if I take a different input, so for example, if I take the input 2, okay, put it through my function, it will then be mapped to an output of 0.5. So does that make sense what's happening here? I'm basically taking a value from my input number line and I'm drawing a line to see where it would end up on the output number line. So the blue circle represents my input, the orange circle represents the output, and then I'm just seeing how they're connected together with this line here. Okay, and you can see that basically as I change my input, okay, you can kind of see how my output is changing. So this is just a way of visualizing my function. Okay, I'm just taking my input and I'm just seeing where it would end up on my output number line. Well, if I do that for kind of a set of values, for every single possible value, say between -5 and 5 over here, then I can actually draw in loads and loads of lines to see where each input corresponds to on the output. So I use that using a mapping, and you get this really beautiful effect which happens. Okay, so all of these green lines just simply represent a connection between an input on the input number line and the corresponding output on the output number line. Okay, so I think this is really, really beautiful. Okay, and this is kind of all I'm literally doing here is a mapping. So I'm taking an input and I'm mapping it to a corresponding output. And if I do that for a set of values, I get something like looks like this. If I try it with different functions, so this is for 1 over x, you kind of get this nice circle, and you can kind of see that as I move it closer to 0, you can see it grows really quickly, okay? Whereas as I move it away from 0, you can see that the output kind of grows slower. So if I try it for different functions then, let's try it for example cosine of x, let's just click that one. And you can see similar kind of thing, I'm just taking loads of inputs and I'm seeing where they're going to end up at on the output number line. So again, really, really pretty and really beautiful. Okay. If I take something funky like sine of 3x plus sine of 2x plus sine of x, I get something that looks like this. Okay, so it looks kind of quite cool again. And if I take something like e to the power of sine squared of x, I'd get something that looks like that. Okay, and I can try various different inputs and outputs if I like. For example, I could just try x squared and I get something that looks like that. Now, what I want to show you, so let's take for example something like cosine of x. Do you notice that for some of these things, so for some of cosine of x and 1 over x, do you notice that there's kind of a range of values that they can only take? So for example, if I take 1 over x, it looks as if values or value with 0 can't be taken as an input, okay? Because there's no value there, there's no value which 0 gets mapped to, and the similar thing on the output. If I take something like cosine of x, do you notice that even though I can put any input I like into this function, it always gets mapped to a value between -1 and 1, right? If I take this funky function like sine of 3 of x plus sine of 2x plus sine of x, do you notice that I can take any input I like, but it always gets mapped to a value between about -2.5 and 2.5, okay? If I take something like x squared, okay, again, I can put any input I like in, but it will always get mapped to what looks like a positive value. In other words, there'll be no negative values on the output. Okay, so I want to describe this relationship. I want to describe the fact that for some functions, you can only put certain values in. For example, 1 over x, you can't put 0 in. That doesn't get mapped to anything, but you can put pretty much any other value in. Or it might be that for cosine of x, I can put any value of in, but it will only get mapped to specific values. So you'll only get specific values out. In this case, values between -1 and 1. I want to describe this idea. I want to describe the idea that you can only put some values in, and so for some functions, you only get certain values out, okay? And I do that by using something called domain and range, okay? So domain and range. So because I have two words here, it makes sense that one of the words corresponds to the values that I can put in, and one of the words corresponds to the values that I get out, okay? So in this case, my domain corresponds to the set of values for my input, okay? So my domain corresponds to the set of values for my input. In other words, my x's, okay? So what values can I physically put into this function? What values can I physically put into this function, okay? Whereas my range corresponds to the set of values for my output, okay? So in this case, my y. So in other words, what values do I get out after I've put my input values into the function, okay? So as an example, okay, if I take a function like f of x equals 1 over x. So if I take my function to be f of x equals 1 over x. Well, let's actually create a quick table here. Okay, so let's suppose I've got a table like this. So it's basically a table with 3 columns. On the left-hand side, I'm going to just give you a function. So in this case, I'm giving you f of x equals 1 over x, okay? Then I just need to figure out what is the domain? What is the set of values for my input? And what's the range? What's the set of values for my output? So in this case, we just saw that on the graph, if I take the graph 1 over x, so I take the function 1 over x, you could see that I could take any value for the input except 0. And I'd also get any value for the output except 0 as well, okay? So the way which I would write that is that if I could take any value except 0, okay, I could literally just write that. So the domain is all real values of x, okay? So x is an element of the real numbers, okay, except 0. So the way which I would write that is with a backslash like so. Okay, so except 0, okay? Now, that's kind of fancy notation. If you've never seen that before, it's not an issue. You could always just write down any real value of x except 0, and that'll be totally fine for your domain. And what's your range? Well, the range is obviously corresponding to the values of y, okay? So again, I can take any real value of y that I like except 0, okay? And we saw that on the graph. If I take my function like cosine of x, so for example, if I take a function like cosine of x, now we saw from the graph with cosine of x, didn't we? So if I now put cosine of x there, you could see that I could put any real value in that I like for my input. So there's no restriction on the values that I can put in for my input. So let's write that. Okay, so my domain is any real value of x. Okay, so x is an element of the real numbers. Or I could simply write any real value of x, that's fine as well. However, you saw that the domain, so the domain is any real value of x, but it always gets mapped to a value on the output between -1 and 1. Okay, so the output is always between -1 and 1. So again, the way which I would write my range, which corresponds to my output, would be that y has to be between -1 and 1. So that's how I'd write that. Okay, so my domain for my cosine of x is any real value I like. I can stick any value I like in, but my range is always to get mapped between -1 and 1. Okay, if I just try one more example here, let's try, for example, f of x equals x squared. Okay, we saw that one together, didn't we? Okay, so just think, maybe you can think about this without physically drawing it. Can I stick any value I like in for x squared, or are there some restrictions over what I can't stick in? Well, I don't think so. I think I can stick any value I like in for x squared. Because if I give you any value, you should always be able to square it. You should always be able to multiply it by itself. So in this case, I would say that x is a member of the real numbers. I can stick any value of x in that I like, okay? But let's think about the range, and it might make sense to have a look again at the mapping. So let's type x squared here. So you saw that with x squared, okay, I could stick any value of x in which I like, but it would always get mapped to a value of y which is greater than or equal to 0. So in other words, no negative values of y could I get out. No output values would be negative. Okay, so the way which I would write that is that y has got to be greater than or equal to 0. Okay, so that would be my range for x squared. So really, with a function, you have two key ideas. You've got the domain, which is the set of input values, and you've got the range, which is the set of output values. Okay, now again, the way which I remember which is which, just think in the same way that x comes before y in the alphabet, have a look at domain and range. Okay, well look, I've got a D and I've got an R. What comes first in the alphabet? The D, therefore it corresponds to X, or the input values, and then R comes afterwards in the alphabet, which means that it corresponds to the Y's, or the output values, okay? So just makes sense. Now, good tip, when you're dealing with domains and ranges, it will come with practice, okay? So as an example, if I give you a function, I'm just going to give it a different name, just to not confuse it with the ones above, okay? So let's suppose I have y equals g of x, and let's suppose my function is something like 1 over x minus 2 times by x minus 4, okay? Well, the question is, can I put any value of x in which I like? So let's figure out what the domain is in this case, okay? So let's figure out what the domain is. The question is, could I put any value of x in which I like? The answer is no, because if you have a think, what's literally happening here is I'm taking 1 divided by something, okay? Now I can do 1 divided by pretty much anything except 0. So I cannot have a denominator of 0. So whatever goes on the denominator, it cannot be 0. Well, just think, I can see two values of x which would make the denominator 0. 2 would make the denominator 0 because of course you have 2 minus 2 then, which would be 0. So in other words, I can say for my domain that x can be any real value I like except, and I'm going to put a couple of different values because there's a couple of different values here. So I'm going to put it in as a curly bracket, okay? So I can't have 2, but also you notice that I can't have 4 either because 4 minus 4 would also be 0. So basically I just need to have a look at this situation, think about it logically and think, whatever happens, I can't have a denominator of 0. So in this case, I can have any real value as long as it's not 2 and as long as it's not 4. So that's how I want you to read that, okay? And you notice I'm just using curly brackets to say it's not 2 and it's not 4, okay? So that's just kind of a way of grouping those together. Another useful technique would be, for example, to draw the graph. If you know what it looks like, draw it. So for example, if I say now y is equal to h of x, and let's suppose my h of x is equal to, let's say, x squared plus 5, okay? Well, let's actually draw what this graph looks like. So fairly obvious it's an x squared graph, so it's a parabola. So let's start off by drawing ourselves a parabola. And then just think, if I take all of my x squared values and add 5, what that simply corresponds to is take this parabola and move it up off the origin, off the vertex where the origin is, up by 5, okay? So in other words, it would look something like this, okay? So that would be the origin, and that would be 5, okay? So that there would be my h of x equals x squared plus 5. It's just simply taking my parabola, x squared, and shifting it up by 5, okay? We'll have a look in this case, okay? Can I stick any real value in for my domain? Yes, I can. I can take any real value I like. I'll always be able to square it and then add 5, okay? So in this case, my domain is any real value of x, okay? But just have a look at the graph to see what my range is doing. Well, just remember that my range is always dealing with my outputs. So in this case, my inputs are x and my outputs are y. So there's my x and there's my y on my graph, okay? Well, just have a look. I'm interested in my range in this case, so I'm interested in the values of y that I can get out. Well, in this case, I can take any value of y so long as it's 5 or above, okay? So as long as it's 5 or above, I can take any output. But anything below 5, it's not allowed. Okay, so I can basically write this as y has got to be greater than or equal to 5. It can't be anything less than 5, and I can see that from the graph. Okay, so sometimes when you're figuring out domains and ranges, okay, sometimes it's a case of thinking about it logically, like we were with that example at the top. Okay, sometimes it's a case of just figuring out what the graph looks like. Now, you've just seen that really I've communicated domains and ranges in two separate ideas. Firstly, I got you to visualize it like this on the screen. So I thought, right, okay, just think about it as two separate number lines, okay? And I'm just simply drawing a connection between the input and the corresponding output for that rule. However, you've probably hardly ever seen it looking like this, okay? But really what I'm doing here is talking about an idea which you are very familiar with and which I've hinted to just a minute ago, but it's just you've thought about it in a slightly different way. So at the moment, this just seems a really inefficient use of space. So you've got the input number line and you've got the output number line separately. So you have to physically draw two number lines which are parallel to each other and then just physically draw like connections between them. It just seems like a really inefficient way of doing it. So what I'm going to do to make a more efficient use of space, I'm going to take my output number line, I'm just going to rotate it through 90 degrees. I think that'll be enough. If I rotate it through 90 degrees, so it's vertical instead of horizontal, I think that'll be enough to differentiate it or distinguish it from my input number line. Okay, so my input number line will be horizontal and my output number line, I'm just going to rotate through 90 degrees, so it's vertical. And that's a way of differentiating between my input number line and my output number line. And I guess because there's a number which is the same on both of these number lines, I could choose any of them. Okay, so I could choose like 0.5 or 1 or 2 or 3 or 4. But I guess 0 seems like an origin place. It seems like a nice place to start. So what I do is when I rotate my output number line through 90 degrees, I'm just going to make sure that the zeros match up. So they intersect at zeros. Let me show you what I mean because it might be easier. So what I'm going to do is I'm just going to take my output number line and rotate it through 90 degrees. And I would get something that looks like that, okay? So I'm just literally, if I just do that again, I'm going to take my output number line, I'm just going to rotate it through 90 degrees. So now it intersects at 0. But you can still see this is still my output number line, okay? Now in actual fact, I'm just going to take something like 1 over x again. So I'm just going to take this mapping. Because you just notice when I rotate my output number line, so it intersects my input number line at 0, you can see that my mapping also still gets mapped. So at the moment, it's still mapping a point on this horizontal line to this vertical line. So my input number line to my output number line, right? But again, this just seems like a really inefficient way of doing this. Now we've got basically two-dimensional space. We've got horizontal movement, which would represent my inputs, and we've got vertical movement, which would represent my outputs. So if I hide that mapping, what I could do, if I just say, for example, that I want to take 1 on my input number line and map it to 1 on my output number line. Well, the way in which I could do that is actually physically use two-dimensional space to do that. So in other words, I could find just a single point that would do that job for me. And this point just means that however far I move left or right, so however far this point is left or right, is just simply how far or what the value of my input is. So in other words, the positioning of the left and right position of this point would be the same as the positioning of my input. So if my input is 1, you can see that it's moved to, it's sort of positioned above the 1. If I move this to 2, you notice that I'm moving it horizontally across, so it's now in line with 2. So in other words, this point, however far it moves left or right, is dictated by whatever the input is. But you also notice that because I've got my output, it's the height of that point that is dictated by the output, okay? So you notice that this point is basically moving. The position left or right, so how far it moves left or right, is dictated by my input, and how far it moves up or down is dictated by my output. Well, if I just connect together all of the points, okay, if I just connect together all of the possible points that I could have for my inputs and outputs, so all of these white dots, if I connect them together, I would get something that looks like this, and you might just be able to see it with the graph, okay? So basically, this line here just represents all of these points, all of the different possible inputs to the corresponding outputs, all joined together, okay? And you can see I get my graph here. So for example, if I just now look at cosine of x, you get a graph that looks like that. If I look at sine of 3 of x plus sine of 2x plus sine of x, you look like that. Now that seems a lot more familiar than what we were doing originally, okay? If I rotated the axes, that's what I started doing, but now as soon as I start doing this, okay, this seems to be a lot more familiar. But it's the same idea. It's just simply saying, here is my input number line, here is my output number line, and then I just have a point where the position left or right is dictated by my input and the position up or down is dictated by my output, okay? So thinking about graphs and functions makes total sense. It's just a way of connecting together input, which is my horizontal number line or my x-axis, to my output, which is my vertical number line or my vertical axis. Now, just to finish off, I want to show you a really important and fundamental function which you need to be aware of. And it's something called the modulus function. Okay? Now, there's a couple of different names for it. You can call it the modulus function, or if you prefer, you can call it the absolute value function. Right. So let's actually see what we mean by the modulus or the absolute value function. Well, it's a really simple function to get your head around. It just simply says, whatever my input is, make it positive. Simple as that. Whatever my input is, make it positive. So if I give you -3, the modulus function will just make that positive, so make it 3. If I give you 7, well, the modulus function will keep it at 7 because that's still positive. If I give you -1,000,000, the modulus function will just turn it into 1,000,000 because it just says just make it positive. So the modulus function or the absolute function or the absolute value function, I should write absolute value function there. So absolute value function, it's a very, very simple function. It just simply says whatever your input is, make it positive. Okay, so the way which we write this, okay, so I could either write make it positive. So make my input positive. That's just simply what the absolute value function means, or the modulus function means. Okay, the way to think about this, okay, the way to write it at least, if I take a function, y equals f of x, I'm just going to say that my function is called f, my input is x, and my output is y. Okay, the way which I would say make my value positive, the notation we use for the modulus or the absolute value function, is simply just this. So my function is quite simply take x and make it positive. So you see these sort of barred lines, these vertical lines each side of my input, that just simply is the absolute value function. It just simply says make it positive. Now, there's 3 ways that we can think about this function, okay? And I'm going to give you all 3. So way 1 that you can think about it is it's the distance from the origin, okay? So if I think about this, if I draw my number line, okay, and if I give you a value, so here's 0 in the middle, and if I give you, for example, 5, okay? Well, the way that I can think about the absolute value of 5, well, if I just make it positive, then fairly obviously, 5 has also got to be positive, so the value has got to be 5. So what that literally means, if I take 5 on my number line, which is there, the absolute value of 5, or the modulus of 5, just simply asks the question, how far away from the origin is it? Well, as you can see, 5 is 5 units away from the origin, okay? So therefore, the absolute value function, the way which you can interpret that, is it's just simply saying it is 5 units away from the origin. But that kind of answers the question, well, why is -5, absolute value, also equal to 5? Because if I look at -5 on my number line, it's over here, okay? If I ask the question, the absolute value of -5 is just simply asking the question, how far away from the origin are we? Well, if you have a look, -5 is also 5 units away from the origin. So the first way that I want you to think about defining the absolute value function is, yes, make my input positive, okay? But what it literally means from a graphical point of view or a visual point of view is it's simply asking the question, how far is my input from the origin? Okay? So the way which I want you to think of this is as distance, okay? It's just simply a distance from the origin. Or a starting position, okay? So it's kind of the first way that I want you to think about the absolute value function, okay? Yes, make my input positive, but how is this actually used? How is this actually applied? Well, it's just simply asking the question, how far is my input from the origin? Okay, how far is my input from the origin? So it's a distance, okay? Now, the second way that I want you to define this absolute value function is just by simply thinking about how can I actually physically make a number positive? Well, the first way that I can do it is by cases, okay? By cases. I can just think about all the different possible cases that I can have for my input, okay? So if I take an input n, okay, and if I ask for what is the absolute value of n, or what is the modulus of n, there's a couple of different options that I can have, okay? I can either say, well, okay, n could be positive to start off with, okay? So if n is positive to start off with, if n is greater than 0, I don't need to do anything to my input, okay? Because it's already positive, the absolute value is just asking for a positive number, so I can just leave it as n, okay? So I can basically interpret it like this, okay? Whereas if n is less than 0, if n is negative, for example like -2 or -5 or -1,000,000, it basically says, what can I do to that value to ensure that that negative value becomes positive? Well, why not multiply it by -1? So in other words, it's just going to be the negative of whatever it was before. So the way to interpret this, if you've never seen this before, is called by cases. This is called a piecewise function. The idea is the absolute value of n can be defined in two different possible cases, okay? The first case, if n is positive, if n is greater than 0, then just leave it as it is. That's the first thing. So the top line, that's how you interpret it. Otherwise, if n is negative, so if n is less than 0, then make it negative, okay? Make it negative, right? So it's basically just considering the two different possible situations you can have. If you have a positive value, leave it as it is. But if it's negative, then you have to make that negative. So the negative of a negative has to make a positive, hence why we write negative n, okay? So cases just simply considers all the different possible cases that you could have for your input, and then it tells you what you need to do with it. So the thing on the right, this thing here, tells you the different possible cases that you could have. So whether it's positive or whether it's negative. Then the thing on the left tells you what you actually need to do to n in order to deal with that particular case, okay? So what do you need to do? So if you like, this is my rule, or this is my function. This is the thing which I actually need to do, okay? Now you notice that I haven't included what if it's 0 there, because to be honest with you, it doesn't matter where 0 is. I can either put 0 in here, because of course if I want to find the absolute value of 0, that's 0, okay? But if I also put it down here, well, the negative of 0 is still 0, okay? So it doesn't really matter where I put 0. Just by convention, I'm just going to put it on the top. So I'm going to include 0 up there just by putting that line down there, okay? But that's the way to interpret this piecewise or cases, okay? Now, the last way that we're going to interpret our absolute value function, okay? The last way is actually by using Pythagoras. So it comes back to the idea of a distance. So just remember that my first sort of situation was looking at it on a number line. It was basically saying how far is my input from the origin, okay? But now what I want to do is actually define this as an actual physical distance. So if you think about it, if I asked for Pythagoras, if I gave you 2 points, let's say here and let's say here, okay? And if I asked you what was the distance between those 2 points, so what was the actual physical straight line distance between those 2 points? Well, the way which you would do that is by looking at the distance across, okay, which you may call A, and then you look at the distance up, which you may call B, and then to find the distance which you're after, you would just simply take A squared, add B squared, and then square root it, okay? Now we're going to use a very similar idea here for distance, okay? If I want to make a value positive, regardless of whether it's positive or negative, I mean, we've just seen with cases that we can always make a value positive or always make a value positive just by considering whether that value was positive to start off with. If it was positive, leave it alone. If it was negative, multiply it by -1. But the only issue with doing that is it kind of defeats the object. Like, what if I don't want to go through and computationally ask the question, is it positive or is it negative every single time? What if I could just apply a get out of jail free card? What if I could just apply a function that would work all the time? It would always make my output positive regardless of whether my input was positive or negative to start off with. So in other words, I don't need to consider, was it positive or negative to start off with? Well, believe it or not, it's using this idea of Pythagoras. What if I just take my value, if I square it, but then immediately square root it? Okay, so you can see that this looks very, very similar to Pythagoras. And actually the reason why we use Pythagoras is because it works. Okay, it always makes my value positive, right? So let's just check. Why does this work? Well, doesn't making a value squared, so if I take a value and if I square it, doesn't the definition of squaring a value literally make something positive? Didn't we just see that with our x squared graph? Okay, if I scroll well the way up here, okay, we just saw with our function x squared that regardless of what value we put in, we can put in any value we like, but the output has always got to be positive or 0. Okay, so actually that deals with 0 automatically for us. So the idea of squaring a number, it will always be positive, right? So it will always be positive. But of course, the issue with squaring a number is that actually it's too big, right? It's out of the realms of what we wanted before, right? If I take 3, for example, and if I square it, it becomes 9. Well, I don't want 9 now, I want 3. So in order to undo that squaring, I need to square root it, okay? So that's the reason. If I square something, I make it positive, immediately square root it, it takes it back to the size that it was before, okay? So as an example, let's just check it. If I take the absolute value of 3 using this new definition, the idea of distance, okay? Well, okay, if I square it, I get 9, but then if I immediately square root it, I get myself back to 3 again. And let's just check it with negative 3, so it doesn't violate our positive number to start off with. Let's just check it with negative 3. We'll have a look. If I take negative 3, and if I square it, well, negative 3 times negative 3 is positive 9. Fantastic, that's what I wanted. Well, then if I square root it again, it will take me back to 3. Now, some of you might be looking at that and going, but don't if I take the square root, I have to take the positive or negative root. Just remember, that is only true if you're coming from something which was squared originally. So for example, if I write down z squared equals 16, you're absolutely right. Here I'm asking the question, what value of z when I square it will give me 16? In that case, it could be z equals 4 or z equals negative 4. So in that case, I need to take the positive or negative root. However, if I ask the question z equals square root of 16, that is a different question to what we asked above, okay? Because now I'm asking the question, what is the square root of 16? It's a different question, right? So in this case, z is just equal to 4. It's just equal to the positive value of z, okay? So this is really important, okay? Just remember that when you square root a number, it is purely positive, okay? So the square root of a number is only positive, okay? Only positive. Whereas if I'm asking a number, if I'm taking a number, squaring it, and then I get 16 out, for example, in that case, I could have positive or negative. We'll have a look. In this case, I'm just simply square rooting it. I don't need to worry about plus or minus. So in this case, it is purely just positive. Okay, so long way round. Let me just summarize exactly what we've got there. So if I take a function, y equals f of x, let's say, and if that function is the absolute value of x, okay, so if that function is the absolute value of x, there's 3 ways that I can define this function. Number 1, it is the distance from the origin. Okay, so it's just simply saying, take my number, see where it is along my number line, and then just ask the question, how far from the origin is that number? Okay, so if I take my number line, there's 0, there's the important point. If I take x is over here, then it's just simply saying, how far from the origin is that number? Okay, or if x was over here, for example, if x was over here, so this would be like negative x, how far away from the origin is that number? Okay, so it's just one way of thinking about the absolute value function is it's the distance away from the origin. The second way that we can think about the absolute value function is by cases, okay? So it simply says that if I want to take the absolute value of x, I need to consider first of all, is it positive or is it negative? Well, if x is positive or 0, I just leave it alone, I leave it as x. If x is negative, I can take the negative of whatever it was before, and then I'm sure that it's going to be positive, okay? And the third way that I can define my absolute value function is by thinking about it as the physical formula for distance. It's by using Pythagoras, okay? So I can basically say the absolute value of x will be equal to square that value, but then immediately square root it. Then that way, case the sort of definition 3, it doesn't matter whether the value was positive or negative to start off with, okay? So that's really, really nice. So let's actually see, what does the graph of y equals the absolute value of x looks like? So let's suppose I actually physically wanted to graph this. We've just seen that graphing functions is really important, okay? It's how we simply visualize it, it's how we get the domain and how we get the range. So how would we actually see what the graph of y equals the absolute value of x looks like? Well, first of all, let's take the graph of y equals x, okay? So let's just not worry about the absolute value sign, let's just take the graph y equals x. Well, the y equals x graph is just simply a graph that looks like that. So that's y equals x, okay? So it's just simply a line that lies at 45 degrees to the input and the output axis, the x and the y axis, okay? Well, the absolute value of x, just remember, just says take whatever your value is and make it positive, okay? So have a look. All these values up here are fine because they're all above the axis. All of my outputs are positive. Okay, but if you have a look, all of the values down here are no good because they're all negative. So all these values over here, the output is positive. All the values over here, so for my negative x values, all of my values will come out as negative. So in other words, my output will be negative. So what could I do? Well, okay, let's just make them positive again. So in other words, I reflect it in the x-axis. So finally, the graph y equals the absolute value of x will just be a graph that looks like this. Okay, so you can basically see that the graph that was going to come down here has just been flipped up to go up there instead. Okay, does that make sense? So what about if I want to deal with something like y equals x minus 2 absolute value? Okay, well just think first of all, what would the graph y equals x minus 2 look like? Let's have a look at that. Okay, well the graph y equals x minus 2 will just simply have a gradient of 1 and a y-intercept of negative 2. So let's have a look at that. It would look something like this. All right, now just have a look. So this is y equals x minus 2, so not absolute value yet. Have a look. Are you happy that it will intersect the y-axis at negative 2? That's what the negative 2 part tells us. That's our y-intercept, right? But are you happy as well that it would cross the x-axis at 2? Have a think. The way to work out the x-intercept is set y to be 0. So if I set y to be 0, I get x minus 2 equals 0, which means that x has to be equal to 2. Okay, so therefore, to get my absolute value graph, all I'm simply going to have to do, anything where it's above the axis, because remember I'm looking for outputs, so anything above the axis, so anything where my output is positive, that's all good. So all that part of the graph is all good. Okay, so I can keep that bit the same. But you notice that anything below the x-axis is going to result in a negative output. That's not what I want. Okay, so I don't want a negative output. So therefore, all I'm going to do is take all of those negative outputs and make them positive again. So the way to do that is by reflecting it in the x-axis, because you notice that all of those negative y values now become positive y values. Okay, so in other words, it's going to flip up here instead, and it's going to intersect up here at 2 instead of at negative 2. Okay, so the overall graph will look something that looks like this. Okay, so that there will be 2, and that there would be 2. Okay, so just think when you're dealing with absolute value graphs, think about what it would look without the absolute values. Okay, so just sketch that graph, then just ask yourself the question, any point which has a negative y value, you've got to make that y value positive. So just simply reflect those points in the x-axis and you'll be away. Okay, so just very quickly to finish off, let's have a go at solving this inequality, which has absolute value symbols in here. Okay, so I'm asked to solve a number, which when I times it by 4 and take away 5, then take the absolute value of it, it should be less than taking that same number, timesing it by 2, adding 1, then taking the absolute value of that. Well, I think the easiest way which we can go about solving this is by thinking about this by cases. Okay, so by thinking about this by cases. So first of all, I need to consider all of the different possible cases that I can have. In fact, just for the sake of time, because I can see we've run out of time just ever so slightly, let's actually remove the absolute value signs from the right-hand side, because it's going to be slightly easier to solve if it's like this. So there's a couple of different ways I can do this. I can either think about this as, on the left-hand side, I can change this to the square root and then square it. Okay, that's one definition I can use, but I'm going to go for by cases. So in other words, there's two different cases that I could have for 4x minus 3. Okay, so I could basically say that 4x minus 3 would just be equal to 4x minus 3 if 4x minus 3 is positive, or 0, I guess. Okay, so as long as it's greater than or equal to 0, I can just treat the 4x minus 3 absolute value as 4x minus 3. However, the other case is that the absolute value of 4x minus 3 will just be the negative of 4x minus 3, or negative 4x plus 3 if you prefer. So in other words, take the 4x minus 3 multiplied by negative 1, and that would be true if the 4x minus 3 was negative. So in other words, there's two different cases that I need to consider, and we've just established that. Okay, so let's solve each situation. So let's first of all go for the red situation. So if 4x minus 3 is positive or greater than 0, I can just treat the absolute value of 4x minus 3 as just 4x minus 3. In other words, I would get 4x minus 3 is less than 2x plus 1, and then I just have to solve this. So let's first of all add 3 to both sides and take away 2x. So I get 2x is less than 4, which means that x has got to be less than 2. Okay, so I've got x is less than 2 as my first inequality. Now the other situation, remember, is that if 4x minus 3 is negative, then I'm going to have to deal with it. So I'm going to have to deal with the absolute value of 4x minus 3 as if it was negative 4x plus 3. So if I do that, I have negative 4x plus 3 is less than 2x plus 1. So you notice all I'm doing there is I'm just substituting the absolute value of 4x minus 3 with the case if it was negative, okay, or if it was positive in the red. Okay, now I can deal with this. Okay, so let me just scroll up so we've got it. So okay, first of all, I'm going to add 4x to both sides and take away 1. So I get 2 is less than 6x. And then what I can do is just swap the sides over. I'll get 6x is greater than 2, which means that x has got to be greater than 2 over 6 or 1 over 3. Okay, so that's the other situation that I can have. Now let's just have a think. How can I combine these two inequalities together? So I have, first of all, x has got to be less than 2. That's the one in red. So let me draw out a number line and let's see if we can visualize this then. So here's 0, okay, here's 0. And first of all, I've got the case that x has got to be less than 2. So I'm going to put 1, actually I'll make it a little bit bigger. So I'm going to put 1 here, I'm going to put 2 here, and I'll maybe just put negative 1 and negative 2 in just for consistency, okay? So the first case that I've got is that x has got to be less than 2. So if it's less than 2, it means I can't include the 2, but I can have anything to the left of that. Okay, just like so. The other case that I've got to satisfy as well is that x has got to be greater than 1/3 at the same time. So here's 1/3, okay, I'll just put 1/3 here. So here's 1/3, okay, it can't be 1/3, but it's got to be anything greater than 1/3. So let's just have a look at that. What region on my number line is shaded by both of these inequalities? Well, are you happy it's anything from negative 1/3 right the way up to 2? Okay, so it's anything from 1/3 right the way up to 2. That's the only portion of the graph that satisfies both of these inequalities. Because sure, anything above 2 is satisfied by the blue inequality, but not by the red. And anything below 1/3 is satisfied by the red inequality, but not the blue one as well. So the only region on the graph that is satisfied by both of these inequalities is the bit between 1/3 and 2, but not including both of these things. So the way which I would write that is that x is between 1/3 and 2, but not including 1/3 and 2. So I'll just write that as 1/3 is less than x, which is less than 2. So that there would be the final solution to the original equation or inequality that I had to solve. So 1/3 is between, so 1/3 is less than x, but x has got to be less than 2. Okay, so that there is my final solution. So if I stick in any value, so as long as it's between 1/3 and 2, but not including those two things, that would satisfy that inequality. Okay, so hopefully that makes sense.